Testing, 1, 2, 3. I think my mic is working. Okay, good. I still don't have an actual microphone to work with. And I came really unprepared today. But it's been 13 days since my last stream. I don't want to have a lazy streak. And something caught my attention yesterday that I was like, oh my god, I have to finish what I'm doing so that I can do that thing that caught my attention yesterday. So yay. Good morning, good evening, good other times of days. Let's jump into it. Yay. So I'll tell you what caught my attention, which after I do the intro. So I've been doing this Introduction to Machine Learning for Coders course for, it's definitely been like over 6 months at least, because I think it was it October, November I started, and now it's May. So it's been a while, but it's mostly like my fault that I'm being slow. So I was just checking this lesson that I'm taking, which is lesson 11, last half. I'll try to finish it today. And then we'll have lesson 12, and then inshallah we'll be done. Yesterday, YouTube recommended me, let me see if I can search, Graham, nope, wrong name, Newberg? Oh shoot, why did I forget his name? He's an NLP researcher, and he has his whole course from, I think it's from Carnegie Mellon University, live, and that really caught my attention. I mean, not live, like his lectures are on YouTube, so that caught my attention. And I have been meaning to take the Hugging Face. Oh my god, they keep creating new stuff. NLP course. So, oh, what? This is crazy. They keep cooking new things. Tropta. Okay. Yeah. And as a preparation, because I felt unprepared, ill-prepared, I tried to run this. Oh my god, it worked. What? Hey. Cool. Like 20 minutes ago, half an hour ago, I tried to run this, and it ran. Because, Jeremy is working here, and I didn't want it to, wow, cool. Regularized logistic regression with trigrams. Cool. So yeah, let's finish the second half of this lesson so that I can do lesson 12 and start something new, because new things are always fun, and finishing things that you promised yourself to finish 7-8 months ago is less so, but still a sense of accomplishment. Will you be able to hear let's see.
So a couple of questions at the break. The first was just for a kind of,
sorry, I do take things to X2 when I normally listen to stuff, but that doesn't make sense on stream, so let's go big.
Questions at the break. Okay. So couple of,
we're back. Let's do this.
Questions at the break. The first was just for a kind of reminder or a bit of a summary as to what's going on here, right? And so here we have W plus, I'm writing it out, yeah, plus
Weights.
adjusted weight, a weight adjustment, times R, right? So normally what we were doing, is saying, hey, logistic regression is basically WX, right? I'm going to ignore the bias, okay? And then we were changing it to be W dot R times X, right? And then we were kind of saying, let's do that bit first, right? Although in this particular case, actually, now I look at it, I'm doing it in this code. It doesn't matter, obviously. In this code, I'm actually doing this bit first. And so, so this thing here actually, I called it W, which is probably pretty bad. It's actually W times X, right? So, so instead of W times X times R, I've got W times X plus a constant times R, right?
The 1.4 was
So the key idea here is that regularization.
What did I do? Nothing, I hope. I was watching the last 10 minutes of my last stream just to remind myself what I was watching. I'm not smart. I mean, I don't remember everything. I'm old. Speaking of old, I fell really badly yesterday and I hurt my leg, but the thing that I'm grateful for is that I didn't break my leg. I just hurt the skin or the part of my leg really, really, really badly, and now it's like a big purple piece of skin. Okay, that was too graphic. Sorry.
Can't draw in yellow. That's fair enough. Regularization wants the weights to be 0, right? Because it's trying to reduce that. Okay. And so what we're saying is okay, we want to push the weights towards 0 because we're saying that's our default starting point expectation is the weights are 0. And so we want to be in a situation where if the weights are 0, then we have a model that makes theoretical or intuitive sense to us, right? This model, if the weights are 0, doesn't make intuitive sense to us, right? Because it's saying, hey, multiply everything by 0, gets rid of all of that, and gets rid of that as well. And we were actually saying, no, we actually think R is useful. We actually want to keep that, right? So instead, we say, you know what? Let's take that piece here and add 0.4 to it, right? So now, if the regularized...
It wasn't 1.4, was 0.4, the constant? 1.4 has been used in other places, I'm sure. I know 4 is supposed to be an unlucky number in I think China, but I think 4 is one of my favorite numbers if you take out some of the odd numbers, because odd numbers are cooler. But 4 is a nice looking number, like a kind number, you know?
Is pushing the weights towards 0, then it's pushing the value of this sum towards 0.4, right? And so therefore it's pushing our whole model to 0.4 times R, right? So in other words, our kind of default starting point, if you've regularized all the weights out altogether, is to say, yeah, let's use a bit of R. That's probably a good idea. Okay. So that's the idea, right? That's the idea. Is basically, what happens when that's 0, right? And you want that to be something sensible, because otherwise, regularizing the weights to move in that direction wouldn't be such a good idea. Okay. Second question was about n-grams. So the n in n-gram can be uni, bi, tri, whatever, 1, 2, 3, whatever grams. So for this movie is good, right? It has 4 unigrams. This movie is good. It has 3 bigrams. This movie is good. It has 2 trigrams. This movie is good. Okay? Can you pass that?
So, yeah, do you mind go back to the W?
I actually have a question about n-gram windows. This movie is movie is good. Okay, that's it. Like we can't do movie. Oh, we can't do is good, and then there's no dot at the end. Fair. Okay, makes sense.
ADJ stuff, the 0.4 stuff. Yeah. So I was wondering if this adjustment will harm the predictability of the model. Because think of extreme case if it's not 0.4, if it's 4,000, and all coefficients will be like essentially.
So exactly. So our prior needs to make sense, and so our prior here, and this is why it's called dot prod NB. Is our prior is that this is something where we think naive Bayes is a good prior, right? And so naive Bayes says that R equals P over, that's not how you write P. P over Q, I have not had much sleep. P over Q is a good prior. And not only do we think it's a good prior, but we think R times X plus B is a good model. That's the naive Bayes model. So in other words, we expect that, a coefficient of 1 is a good coefficient, not 4,000. Right? So we think, specifically, we think 0 is probably not a good coefficient, right? But we also think that maybe the naive Bayes version is a little overconfident, so maybe 1's a little high. So we're pretty sure that the right number, assuming that our naive Bayes model is appropriate, is between 0 and 1.
No, but what I was thinking is as long as it's not 0, you are pushing those coefficients that are supposed to be 0 to something not 0 and make the high coefficients less distinctive from the low coefficients.
Well, but you see, they're not supposed to be 0. They're supposed to be R. Like that's what they're supposed to be. They're supposed to be R, right? And so, and remember, this is inside our forward function, so this is part of what we're taking the gradient of, right? So it's basically saying, okay, we're still going to, you can still set self.w to anything you like, but just the regularizer wants it to be 0. And so all we're saying is, okay, if you want it to be 0, then I'll try to make 0 be, give a sensible answer. That's the basic idea. And nothing says 0.4 is perfect for every data set. I've tried a few different data sets, and
I think 0.4 is perfect for everything. Okay, go ahead.
Found various numbers between 0.3 and 0.6 that are optimal, but I've never found one where 0.4 is less good than 0, which is not surprising. And I've also never found one where 1 is better, right? So the idea is this is a reasonable default, but it's another parameter you can play with, which I kind of like, right? It's another thing you could use grid search or whatever to figure out for your data set what's best. And, really the key here being every model before this one, as far as I know, has implicitly assumed it should be 0, because they don't have this parameter, right? And, by the way, I've actually got a second parameter here as well, which is the same thing I do to R, is actually divide R by a parameter, which I'm not going to worry too much about it now, but again, it's another parameter you can use to kind of adjust what the nature of the regularization is. And I mean, in the end, I'm a empiricist, not a theoretician. I thought this seemed like a good idea. Nearly all of my things that seemed like a good idea turned out to be stupid. This particular one gave good results, on this data set and a few other ones as well. Okay, could you pass that? Oh, you want to start there? Yeah.
Yeah, I'm still a little bit confused about the W plus W adjusted thing. So you mentioned that we do W plus W adjusted so that the coefficients don't get set to 0, that we place some importance on the priors. But you also said that the effect of learning can be that W gets set to a negative value, which effectively turns W plus W to 0. So if we are allowing the learning process to indeed set the priors to 0,
not the priors, the coefficients, yep.
Then why is that in any way different from just having W?
Great question. Because of regularization, because we're penalizing it by that, right? So in other words, we're saying, you know what? If the best thing to do is to ignore the value of R, that'll cost you. You're going to have to set W to a negative number, right? So only do that if that's clearly a good idea. Unless it's clearly a good idea, then you should leave it where it is. That's the only reason. All of this stuff we've done today is basically entirely about, maximizing the advantage we get from regularization and saying regularization pushes us towards some default assumption, and nearly all of the machine learning literature assumes that default assumption is everything's 0. And I'm saying, it turns out, it makes sense theoretically and turns out empirically that actually you should decide what your default assumption is, and that'll give you better results.
So would it be right to say that in a way putting an additional hurdle in along the way towards getting all coefficients to 0. So it will be able to do that if it is really worth it.
Yeah, exactly. So I'd say like the default hurdle without this is making a coefficient non-zero is the hurdle. And now I'm saying no, the hurdle is making a coefficient not be equal to 0.4r. Yeah, that's the difference.
So this is sum of w square into c.
Sum of
Into some lambda or c penalty constant.
yeah, times something.
So the weight decay should also depend on the value of c. If it is very less, like if c is...
Sorry, by c do you mean this? A?
Yeah, a.
Yeah.
So if a is 0.1, then the weights might not go towards 0.
Yes.
Then we might not need weight decay. So
well, whatever this value, I mean, if the value of this is 0, then there is no regularization, right? But if this value is higher than 0, then there is some penalty, right? And presumably we've set it to non-zero because we're overfitting, so we want some penalty. And so if there is some penalty, then my assertion is that we should penalize things that are different to our prior, not that we should penalize things that are different to 0. Right? And our prior...
Some of this stuff is just going right above my head, but I will continue listening.
Is that things should be, around about equal to r. Okay, let's move on. Thanks for the great questions. I want to talk about embedding. I said pretend it's linear. And indeed we can pretend it's linear. Let me show you how much we can pretend it's linear. As in nn.linear, create a linear layer.
Okay.
Here is our data matrix, right? Here are our coefficients if we're doing the R version. Here are our coefficients R, right? So if we were to put those into a column vector, like so, right? Then we could do a matrix multiply of that by that, right?
Okay.
And so we're going to end up with, so here's our matrix, here's our vector, right? So we're going to end up with 1 times 1 plus 1 times 1, 1 times 1, 1 times 3. Right? 0 times 1, 0 times...
Is my stream not good? Should be fine. Internet is okay, not perfect, but pretty okay. Okay.
times 0.3. Right? And then the next one, 0 times 1, 1 times 1, so forth. Okay? So like the matrix multiply, of this independent variable matrix by this coefficient matrix is going to give us an answer. Okay? So that is just a matrix multiply. So the question is like, okay, well, why didn't Jeremy write nn.linear? Why did Jeremy write nn.embedding? And the reason is because, if you recall, we don't actually store it like this, because this is actually of width 800,000 and of height 25,000. Right? So rather than storing it like this, we actually store it as 0, 1, 2, 3. Right? 1, 2, 3, 4. 0, 1, 2, 5. 1, 2, 4, 5. Okay, ignore the ones one. Oops. That's actually how we store it. Right? Is this bag of words contains which word indexes? Does that make sense? Okay, so that's like this is like a sparse way of storing it. Right? It's just list out the indexes in each sentence. So given that, I want to now do that matrix multiply that I just showed you to create that same outcome, right? But I want to do it from this representation. So if you think about it, all this is actually doing is it's saying a one-hot, this is basically one-hot encoded, right? It's kind of like a dummy matrix version. Does it have the word this? Does it have the word movie? Does it have the word is? And so forth. So if we took the simple version of like, does it have the word this? 1, 0, 0, 0, 0, 0, right? And we multiplied that by that, right? Then that's just going to return the first item.
Oh, yeah.
That make sense?
If it's 0, then we get 0. Makes sense, of course.
So in general, a one-hot encoded vector times a matrix is identical to looking up that matrix to find the nth row in it, right? So this is identical to saying find the 0, 1st, 2nd, and 5th coefficients, right? So they're the same. They're exactly the same thing. And like it doesn't, like in this case, I only have one coefficient per feature, right? But actually, the way I did this was to have one coefficient per feature for each class, right? So in this case, it's both positive and negative. So I actually had kind of like an R positive and an R negative. So R negative would be just the opposite, right? Equals that divided by that, right? Now in the binary case, obviously it's redundant to have both, but what if it was like, what's the author of this text? Is it Jeremy or Savannah or Terence, right? Now we've got 3 categories. We want 3 values of R, right? So the nice thing is that in this sparse version, you can just look up, the 0th and the 1st and the 2nd and the 5th, right? And again, it's identical, mathematically identical to multiplying by a one-hot encoded matrix. But when you have sparse inputs, it's obviously much, much more efficient. So this computational trick, which is mathematically identical to, not conceptually analogous to, mathematically identical to multiplying by a one-hot encoded matrix, is called an embedding, right? So I'm sure you've all heard, or most of you probably heard about embeddings, like word embeddings, word to vec or glav or whatever. And people love to make them sound like there's some amazing new complex neural net thing, right? They're not. Embedding means make a multiplication by a one-hot encoded matrix faster by replacing it with a simple array lookup. Okay, so that's why I said you can think of this as if it said self.w equals nn.linear nf plus 1 by 1, right? Because it actually does the same thing, right? It actually is a matrix with those dimensions. This actually is a matrix with those dimensions, right? It's a linear layer. But it's expecting that the input we're going to give it is not actually a one-hot encoded matrix, but it's actually a list of integers, right? The indexes for each word or for each item. So you can see that the forward function in fast.ai automatically gets, for this learner, the feature indexes, right? So they come from the sparse matrix automatically. NumPy makes it very easy to just grab those indexes. Okay, so in other words, we've got a list of each word index of the 800,000 that are in this document, and so then this here says look up each of those in our embedding matrix, which has got 800,000 rows, and return each thing that you find. Okay, so mathematically identical to multiplying by the one-hot encoded matrix. Does that make sense? So that's all an embedding is, and so what that means is we can now handle building any kind of model, like a, whatever kind of neural network, where we have potentially very high cardinality categorical variables as our inputs. We can then just turn them into a numeric code between 0 and the number of levels. And then we can learn a linear layer from that, as if we had one-hot encoded it, without ever actually constructing the one-hot encoded version, and without ever actually doing that matrix multiply. Okay? Instead, we will just store the index version and simply do the array lookup. Okay? And so the gradients that are flowing back, basically in the one-hot encoded version, everything that was a 0 has no gradient. So the gradients flowing back is just going to update the particular row of the embedding matrix that we used. Okay? And so that's fundamentally important for NLP, just like here. I wanted to create a PyTorch model that would implement this ridiculously simple little equation, right? And to do it without this trick would have meant I was feeding in a 25,000 by 800,000 element array, which would have been kind of crazy, right? And so this trick allowed me to write, I just replaced the word linear with embedding, replace the thing that feeds the one-hot encodings in with something that just feeds the indexes in, and that was it. That it kept working, and so this now trains, in about a minute per epoch. Okay. So what we can now do is we can now take this idea and apply it not just to language, but to anything, right? For example, predicting the sales of items at a grocery. Yes, can you pass that?
Just a quick question. So we are not actually looking up anything, right? We are just saying that now that array with the indices, that is the representation.
So so we are doing a lookup, right? The representation that's being stored for the bag of words is now not 111001, but 0125, right? And so then we actually have to do our matrix product, right? But rather than doing the matrix product, we look up the 0th thing and the first thing and the second thing and the 5th thing.
So that means we are still retaining the one hot encoded matrix.
No, we didn't. There's no one hot encoded matrix used here. Here's the one hot encoded matrix, which is not currently highlighted. We've currently highlighted the list of indexes and the list of coefficients from the weight matrix. Does that make sense?
Yeah.
Great. Okay. So what we're going to do now is we're kind of going to go a step further and saying, like, let's not use a linear model at all. Let's use a multi-layer neural network, right? And let's have the input to that potentially be include some categorical variables, right? And those categorical variables we will just have as numeric indexes. And so the first layer for those won't be a normal linear layer, there'll be an embedding layer, which we know behaves exactly like a linear layer mathematically. And so then our hope will be that we can now use this to create a neural network for any kind of data, right? And so there was a competition on Kaggle a few years ago called Rossmann, which is a German grocery chain, where they asked to predict the sales of items in their stores, right? And that included a mixture of categorical and continuous variables. And in this paper by Gore and Burkhan, they described their third place winning entry, which was much simpler than the first place winning entry, but nearly as good, but much, much simpler because they took advantage of this idea of what they call entity embeddings. In the paper, they thought, I think, that they had invented this. Actually, it had been written before earlier by Yoshio Bengio and his co-authors in another Kaggle competition, which was predicting taxi destinations. Although I will say I feel like Gore went a lot further in describing how this can be used in many other ways. And so we'll talk about that as well. So this one is actually in the deep learning 1 repo. Okay, DL1 lesson 3. Okay, because we talk about some of the deep learning specific aspects in the deep.
Oh, huh. I thought he already talked about this once more. Might be wrong.
Learning course. Whereas in this course we're going to be talking mainly about the feature engineering, and we're also going to be talking about kind of this embedding idea. So let's start with the data, right? So the data was store number 1 on the 31st of July 2015 was open. They had a promotion going on. It was a school holiday. It was not a state holiday, and they sold 5,263 items. So that's the key data they provided. And so the goal is obviously to predict sales in a test set that has the same information without sales. They also tell you that for each store, it's of some particular type. It sells some particular assortment of goods. Its nearest competitor is some distance away. The competitor opened in September 2008. And there's some more information about promos. I don't know the details of what that means. Like in many Kaggle competitions, they let you download external data sets if you wish, as long as you share them with other competitors. So people, they also told you what state each store is in. So people downloaded a list of the names of the different states of Germany. They downloaded a file for each state in Germany for each week, some kind of Google Trend data. I don't know what specific Google Trend they got, but there was that. For each state, they downloaded a whole bunch of temperature information. That's it. And then here's the test set. Okay. So, I mean, one interesting insight here is that there was probably a mistake in some ways for Rossmann to design this competition as being one where you could use external data, because in reality, you don't actually get to find out next week's weather or next week's Google Trends, But, when you're competing in Kaggle, you don't care about that. You just want to win, so you use whatever you can get. So let's talk first of all about data cleaning. You know, there wasn't really much feature engineering done in this third place winning entry. Like particularly by Kaggle standards, where normally every last thing counts. This is a great example of how far you can get with a neural net. And it certainly reminds me of the claims prediction competition we talked about yesterday, where the winner did no feature engineering and entirely relied on deep learning. The laughter in the room, I guess, is from people who did a little bit more than no feature engineering in that competition. So, you know, I should mention, by the way, like, I find that bit where, like, you work hard at a competition and then it closes and you didn't win and the winner comes out and says, this is how I won. Like, that's the bit where you learn the most, right? Like, sometimes that's happened to me and it's been like, oh, I thought of that. I thought I tried that. And then I go back and I realize I like had a bug there. I didn't test properly. And I learned like, oh, okay, like I really need to learn to like test this thing in this different way. Sometimes it's like, oh, I thought of that, but I assumed it wouldn't work. I've really got to remember to check everything before I make any assumptions. And, you know, sometimes it's just like, oh, I did not think of that technique. Wow, now I know it's better than everything I just tried. Because like otherwise somebody says like, hey, you know, here's a really good technique. You're like, okay, great. Right? But when you spent months trying to do something and like somebody else did it better by using that technique, that's pretty convincing. Right? And so like it's kind of hard, like I'm standing up in front of you saying, here's a bunch of techniques that I've used and I've won some Kaggle competitions and I've got some state-of-the-art results, but it's like, that's kind of secondhand information by the time it hits you, right? So it's really great to, yeah, try things out. And also like, it's been kind of nice to see.
When it comes to competitions, I think the first hour is where you take the most of the time and waste time, and is like the most important thing ever, because like that's when you need to think and then you get to apply. But all of the competitions I've done, hash code stuff, has been like 4 hours. So by the third hour, if you're not somewhere, then you're done for. Fun stuff.
Particularly I've noticed in the deep learning course, quite a few of my students have, you know, I've said like, this technique works really well, and they've tried it, and they've got into the top 10 of a Kaggle competition the next day, and they're like, okay, that counts as working really well. So yeah, Kaggle competitions are
Fun.
Helpful for lots and lots of reasons, but you know, one of the best ways is what happens after it finishes. And so definitely, like, for the ones that are now finishing up, make sure you watch the forums, see what people are sharing in terms of their solutions, and you know, if you want to learn more about them, like, feel free to ask the winners, like, hey, could you tell me more about this or that? People are normally pretty good about explaining.
Helpful.
Yeah. And then ideally, try and replicate it yourself, right? And that can turn into a great blog post, you know, or a great kernel, is to be able to say, okay, such and such said that they used this technique. Here's a really short explanation of what that technique is, and here's a little bit of code showing how it's implemented, and you know, here's the result showing you can get the same result. That can be a really interesting write-up as well. Okay, so you know, it's always nice to kind of have your data reflect, like, I don't know, be as kind of easy to understand as possible. So in this case, the data that came from Kaggle used various, you know, integers for the holidays. We can just use a Boolean of like, was it a holiday or not? So like, just clean that up. We've got quite a few different tables. We need to join them all together, right? I have a standard way of joining things together with pandas. I just use the pandas merge function. And specifically, I always do a left join. So who wants to tell me what a left join is?
I do.
Since it's there, why don't you go ahead?
Take everything from the first and add what's on the second. Join what's on the second.
So you retain all the rows in the left table, and so you have a key column, you match that with the key column in the right side table, and you just merge the rows that are also.
You know what surprises me? Is that in a class like this, he asks questions about what's a left join, and he talks about stuff that are going over my head. But like, for me, a left join is something that like is simple, but it's cool that he asks all questions, you know.
Present in the right side table.
Yeah, that's a great explanation. Good job. I don't have much to add to that. The key reason that I always do a left join is that after I do the join, I always then check if there were things in the right-hand side that are now null, right? Because if so, it means that I missed some things. I haven't shown it here, but I also check that the number of rows hasn't varied before and after. If it has, that means that the right-hand side table wasn't unique. Okay, so even when I'm sure something's true, I always also assume that I've screwed it up, so I always check. So I can go ahead and merge the state names into the weather. I can also, if you look at the Google Trends table, it's got this week range, which I need to turn into a date in order to join it, right? And so the nice thing about doing this in Pandas is that Pandas gives us access to, all of Python, right? And so, for example, inside the series object is a .str attribute that gives you access to all the string processing functions. Just like cat gives you access to the categorical functions, DT gives you access to the datetime functions. So I can now split everything in that column. And it's really important to try and use these pandas functions because they're going to be vectorized, accelerated through, often through SIMD, at least through, C code. So that runs nice and quickly, right? And then, as per usual, let's add date metadata to our dates. In the end, we're basically denormalizing all these tables. We're going to put them all into one table. So in the Google Trend table, there was also, there were mainly trends by state, but there was also trends for the whole of Germany. So we kind of put the Germany, the whole of Germany ones into a separate data frame so that we can join that. So we're going to have like Google Trend for this state and Google Trend for the whole of Germany. Okay. And so now we can go ahead and start joining both for the training set and for the test set, and then for both check that we don't have zeros. My merge function, I set the suffix, if there are two columns that are the same, I set the suffix on the left to be nothing at all, so it doesn't screw around with the name, and the right-hand side to be _y. And in this case, I didn't want any of the duplicate ones, so I just went through and deleted them. Okay. And then we're going to, in a moment, we're going to try to create a competition. The main competitor for this store has been open since some date. Right? And so you can just use pandas to date time, passing in the year, the month, and the day. Right? And so that's going to give us an error unless they all have years and months. So we're going to fill in the missing ones with a 1900 and a 1. Okay. And then what we really want to know is like how long has this store been open for at the time of this particular record. Right? So we can just do a date subtract. Okay. Now, if you think about it, sometimes the competition opened later than this particular row. So sometimes it's going to be negative, and it doesn't probably make sense to have negatives, meaning like it's going to open in X days time. Now, having said that,
some stores that were open were already competition for you.
Would never put in something like this without first of all running a model with it in and without it in, right? Because like our assumptions about the data very often turn out not to be true. Now, in this case, I didn't invent any of these pre-processing steps. I wrote all the code, but it's all based on the third place winner's GitHub repo, right? So knowing what it takes to get third place in the Kaggle competition, I'm pretty sure they would have checked every one of these pre-processing steps and made sure it actually improved their validation set score. Okay. So what we're going to be doing is creating a neural network where some of the inputs to it are continuous and some of them are categorical. And so what that means in the neural net that we have, we're basically going to have this kind of initial weight matrix, right? And we're going to have this input feature vector, right? And so some of the inputs are just going to be plain continuous numbers, like, what's the maximum temperature here, or what's the number of kilometers to the nearest store. And some of them are going to be one hot encoded, effectively, right? But we're not actually going to store it as one hot encoded. We're actually going to store it as the index, right? And so the neural net model is going to need to know which of these columns should you basically create an embedding for, which ones should you treat as if they were kind of one hot encoded, and which ones should you feed directly into the linear layer, right? And so we're going to tell the model when we get there which is which, but we actually need to think ahead of time about like which ones do we want to treat as categorical and which ones are as continuous. In particular, things that we're going to treat as categorical, we don't want to create more categories than we need, right? And so let me show you what I mean. The third place getters in this competition decided that the number of months that the competition was open was something that they were going to use as a categorical variable, right? And so in order to avoid having more categories than they needed, they truncated it at 24 months. They said anything more than 24 months, I'll truncate to 24. So here are the unique values of competition months open.
So anything over 2 years is fine? I mean, if you have more power, you can go for like, I don't know, more than 2.
And it's all the numbers from 0 to 24, right? So what that means is that there's going to be, an embedding matrix that's going to have basically an embedding vector for things that aren't open yet, for things that are open a month, for things that are open 2 months, and so forth. Now, they absolutely could have done that as a continuous variable, right? They could have just had a number here, which is just a single number of how many months has it been open, and they could have treated it as continuous and fed it straight into the initial weight matrix. What I found, though, and obviously what these competitors found, is where possible, it's best to treat things as categorical variables, right? And the reason for that is that, like, when you feed something through an embedding matrix, you basically it means every level can be treated like totally differently, right? And so, for example, in this case, whether something's been open for 0 months or 1 month is like really different, right? And so if you fed that in as a continuous variable, it would be kind of difficult for the neural net to try and find a functional form that kind of has that big difference. It's possible because neural nets can do anything, right? But you're not making it easy for it. Whereas if you used an embedding, treated it as categorical, then it'll have a totally different vector for 0 versus 1, right? So it seems like, particularly as long as you've got enough data, that treating columns as categorical variables where possible is a better idea. And so when I say where possible, that kind of basically means like where the cardinality is not too high. So if this was like, the sales ID number that was like uniquely different on every row, you can't treat that as a categorical variable, right? Because, it would be a huge embedding matrix and everything only appears once. Or ditto for like kilometers away from the nearest store to 2 decimal places, you wouldn't make a categorical variable, right? So that's kind of the rule of thumb that they both used in this competition. In fact, if we scroll down to their choices, here is how they did it, right? Their continuous variables were things that were genuinely continuous, like number of kilometers away to the competitor, the temperature stuff, right? The number, the specific number in the Google trend, right? Where else, everything else basically they treated as categorical. Okay. Okay, so that's it for today. So yeah, next time we'll finish this off. We'll see how to turn this into a neural network, and yeah, kind of wrap things up. So see you then.
Oh, cool, great, cool. Where's my mouse? Lesson 11 is done. I didn't do yeah, I'm still here. I didn't do this part, and I know we're using the dot product naive Bayes learner here. Issue is I don't know what I'm doing it for. Why is it 0.2? Oh, wait, what? What happened? Did we just lose everything? No? You did not just refresh, basically. Okay, let's just look what lesson 12 might be, and then we're going to take it next time. Put everything we've learned together to create a model for the Rossmann dataset, including both categorical and continuous features, and careful feature engineering for all columns. Second half, ethical issues that arise when implementing ML models, and why they matter, and ways of thinking them. This is the most important part of the course, so look out for that. Okay. That was easier than expected. I don't know why lesson 11 has been like a monster for me. Not in a bad way though. Like in a funny way, where I'm like, oh, I need to be prepared to finish this lesson. I need to be prepared to finish this lesson. I'm like, what for? I don't even know. Okay. Thank you for joining me. Let me see if I can find that thing that I was telling you about. I know his name is Graham, and it's Newberg. What? Did I find him? Hell yeah, I did. Dang, here it is. He's a face I've seen on Twitter quite a lot, so I trust him. And if you see, we have Advanced NLP Spring 2024, so it's pretty updated. And funny part, started 3 months ago. It's 20 videos. That's crazy. That's so many classes. 20 classes. Who does that? How many classes are there in a semester? I don't know. Maybe it's almost ending. And oh, there was a website. If you click one of them, don't. I don't want to go. Not yet. There's a website, and I think there are assignments, which is, I don't know if we'll have access to them or not. That's as far as I've done with my investigation, because that one is also really why didn't I press it? Okay, it's also really inviting because everything is, I think, inside here. So yeah, all of that fun is waiting for us, so we're gonna do that. Thank you so much. I just became chat. Thank you so much for watching, and see you next time. Would that be tomorrow? I don't know. Let's see. I'm ending the stream, which actually is good now. Frame rate is great. Proud of myself. In 5, 4, 3, 2, 1, and goodbye.